All right, so here's an example of graphing a cotangent graph with multiple transformations, as you can see here. So the first thing that we need to go through and do is realize that the period of a tangent or cotangent graph is different than all of the rest of our trigonometric functions, and the period of it is only pi radians. Now, the other thing we need to consider is that we know, or you should know, that cotangent and tangent graphs contain undefined areas that are represented by asymptotes. So that is generally the easiest place to start and end one period. So we need to consider when cotangent is going to be undefined. So I'm going to do that right down here. Now, cotangent of any theta, any angle, is equal to x over y. So really, if we want to figure out where to start, we simply need to find a point or an angle, a point that represents an angle where y is equal to 0. Now, if you go around the unit circle, you should see immediately that at 0 radians, or right at the start, we are at the point 1, 0. Meaning that x is equal to 1 and y is equal to 0. Well, that means that we're going to want to start at 0 radians, since we know that cotangent will be equal to 1 over 0 at 0 radians. So I'm going to go over to my unit circle special angles, and I'm going to change a couple things on here. One is I know that I'm not dealing with sine, so I'm going to go ahead and change that to cotangent. Another thing that I've adjusted on these in the past is these unit circle special angles we can kind of think of as theta. And then I'm going to go ahead and say, well, I know that I'm still going to start at 0, so it's still a good starting point, but my period is no longer 2 pi long. I'm only going to go up to pi. Now, you can see here that there's a couple ways to look at this. One, I divided that 2 pi by 2, so I'm going to go ahead and divide all of these by 2 in the end. But another way to look at it is I'm taking a period of pi, and just as these were basically the quarter marks of a unit circle, and we can see it here, is that 0 to pi over 2 is 1/4 of my axis. Pi over 2 to pi is is also a quarter. Pi to 3 pi over 2 is another quarter, and then before I change this to 2 pi, or down to pi, 3 pi over 2 to 2 pi is one last quarter. So really, I just want to cut this into quarters. So if I'm going from 0 to pi, then hopefully you can do some quick calculations. Just realize that I just want to change this to pi over 4. This is going to be pi over 2. And this is going to be 3 pi over 4. So that I'm going up by an even amount, or an equal amount, every single time I go from one of my special angles to the next. Okay? So now I have one period here for what would work for cotangent if it didn't have any transformations. So now I'm going to need to use this box here to determine what is happening to my graph vertically, okay, up and down. The A is going to tell me how much my graph is going to stretch, so basically get almost taller is a way you could think of it, or shorter. And then the D is going to tell me how much my graph is going to shift up or down. And we can see that in that the 2 is going to be multiplied by whatever cotangent ends up being. So that'll make it bigger by the same amount no matter what the value is. Now the 1 is going to be added after we multiply that 2. So it'll shift every single point up one value. So what we're going to do is we're going to take every single cotangent value that we get and multiply it by 2, and then we're going to add 1. 2 times plus 1. 2 times it plus 1. 2 times it plus 1. And 2 times it plus 1 once again. Now, as we move on to the next piece, what I'm going to do is, for these parts here, I'm basically just going to say, well, what is cotangent of 0? What is cotangent of pi over 4? Okay. And so on and so forth. Cotangent of pi over 2. Cotangent of 3 pi over 4. And lastly, cotangent of pi. Now, if I go through and calculate out these values, well, cotangent of 0, we already determined that we're going to be at the point 1, 0 there. So cotangent of 0 is undefined. Cotangent of pi over 4, well, that's going to be a 45, 45, 90 triangle, so I know x over y is simply going to be square root of 2 over square root of 2 over 2, so this is just 1. Then here I'm going to have cotangent of pi over 2. I'm going to be at 0, and you can calculate all of these based off of the trig identity. Cotangent of theta is equal to x over y and going around the unit circle. Cotangent of 3 pi over 4, okay, is equal to negative 1, and then we're undefined again when we get to pi. So now if I want my y values, what I'm going to do is I'm just going to multiply this out, following order of operations. Well, this one's undefined, so it doesn't really matter what I add or multiply it by. It's just going to remain undefined. Then I have 2 times 1 is 2, plus 1 is going to get me 3. Then I have 2 times 0 plus 1 is just going to be 1. 2 times negative 1 is negative 2, plus 1 is just going to be negative 1. And then we're undefined again. And if you notice, all of our values, okay, and what we just did is we amplified all of them by 2, and then we shifted them up by 1. So if I want to write down my vertical transformations, okay, I would say that I had a vertical stretch of basically times 2. Okay, so I stretched my graph out vertically, and then I had a vertical shift of plus 1. So those would be my transformations. You can see those right down there. Now the next piece, okay, is going to be to figure out how my x value shifted, because if I just look at where the vertical parts shifted, those are corresponding with my normal unit circle special angles. But I'm also going to have some shifts with the x's, and I can see that here. Now the way we calculate those out is what we more or less want to know is that we know that if we input a 0 into the cotangent trig function, then we're going to get undefined. So we really want to know when 3x plus pi over 2 is equal to, in this case, 0. Now, I don't really just want one rule that works for each, or I don't want individual rules that work for a particular angle. I want one that works for all of them. That's why I labeled this as being theta. So if I consider this to be generic, then I just need to determine when 3x plus pi over 2, or what I'm inputting into cotangent, is going to be equal to whatever theta happens to be. Now, to get that to happen, what we're going to do is subtract pi over 2 from both sides. So that leaves me with 3x is equal to theta minus pi over 2. Then I'm going to multiply both sides of it times 1/3. That'll cancel this out, and I'll just be left with x. And then I have to do it to this side as well. And if you notice, when I multiply it, I'm multiplying the entire side by 1/3. So I get that x is equal to theta, whatever our theta value is here, minus pi over 2 times, all of that times 1/3. And so that's what we're going to do over here. We're going to take theta, or in this case 0, and subtract pi over 2. And we're going to do that each and every time. And what that's doing is that's shifting our graph pi over 2 to the left was all of our values that would normally be at 0, pi over 4, pi over 2, 3 pi over 4, and pi are being moved by pi over 2. Okay. And then we're going to go ahead, and with all of these, we're going to take the entire thing after we multiply all of this out, or I'm sorry, subtract this out, and we're going to multiply that by 1/3. And what that's doing, okay, that is making our period 1/3 the length as it usually is. Okay, so the period is 1/3 the length, okay, it normally is. And hopefully I didn't get on my graph too much there. Okay. Now if we go ahead and go through this process, then we're going to get that this is negative pi over 6. This value right here, well, that would be pi over 4 minus pi over 2 is just negative pi over 4. Okay, in which case we're going to get negative pi over 12. Now here I'm going to have negative, or I'm going to just have 0 times 1/3 is just 0. Then here we have, I did that one right? Yeah. Here we have 3 pi over 4 minus pi over 2. So 3/4 of pi minus the half pi is just going to give us pi over 4. Oh, sorry, times this is going to be pi over 12. And then lastly, and hopefully you can kind of guess what this one's going to be because we can kind of see it mirroring here, is that we have pi over 2 times 1/3, which is just going to be pi over 6. Now, these are our coordinates for one full period. And if we want to verify our prediction about how long a period is, we can simply take the beginning of the period up here and subtract that from the end of the period. Now, we said it was going to be pi, or it was going to be 1/3 of what it normally is. So the period is normally, okay, pi, and we said it's going to be 1/3 of that, or we just divide it by 3, in which case the period is pi over 3. Now we can verify that by taking pi over 6 minus pi over 6, okay, in which case we're going to get, or I'm sorry, minus negative pi over 6, sorry, pi over 6 minus negative pi over 6, and we are going to get plus 2 pi over 6, which would be reduced down to pi over 3. So we can see that this is one full period, and we verified that by 2 different ways. Now we just have to go and plot our values. Now, I'm going to make a quick check here and see that I start at negative pi over 6, and it seems like every one of my values is actually increasing. This might be a little hard to tell by negative pi over 12. Now, another way to just simply look at it is I'm going to go from negative pi over 6, and so I can just maybe make that like right about here, okay, negative pi over 6, and I'm going to go all the way up to pi over 6, and those are obviously on the same distance here from the origin. Okay. Okay, and then I am still going to be cutting this into quarters. Now you can always just count up and know that this is, or negative pi over 12 is half of pi over 6, so it's going to go here. But then we can also see that if we want to cut this into quarters, we're going to put 3 equally spaced, and one of them is going to be at the origin, dashes right in between our 2 endpoints. Because now we have 1, 2, 3, 4 pieces. That's actually a trick that allows you to do all of these, whether it be tangent, cotangent, sine, cosecant, any of them. You can simply find the period, cut it into quarters, and then know how the values normally lie out. I'm going to go ahead and just plot these points, but I wanted to give that pointer. All right, so we're going to start at negative pi over 6, and I see that my graph is undefined there. Okay. And then the next point we go over to is going to be the next quarter, which is negative pi over 12. Okay. And for that one, we're up at 3, so I'm going to go up to 1, 2, 3. I just go right up here. Now, one of the things I would say is I probably made a little bit of a mistake in making my graph so wide here, because my graph is probably going to be a little unruly as far as the way that I actually end up drawing it out. But bear with me, and I'll try to make it obvious how it probably would have been better off to squish it a little bit. But it'll still more or less be, it'll still be right. It just probably would look better if I did otherwise. So anyway, let's go kind of backtrack since I got a little distracted there. We went from negative pi over 6, it was undefined. Then we went over to negative pi over 12, and we're up at 3. Then we go to 0, and we're at 1. Oh, and let me move up here a little bit. And then we go to pi over 12, which is just right here. And we're going to be at negative 1. And if I draw my values out here the same way, negative 1, negative 2, and let's call that 3. Then we're going to be at, oop, did I do that right? Yeah, I'm sorry. So this one here will be at negative 1. So it would just be right here. Okay. Okay. And then the very last point, pi over 6 is going to be undefined. So now you need to realize that obviously the graph is going from its greatest part, which is what cotangent does, and going down to its smallest part. And it looks like kind of like a curve like this. And again, this is why my graph probably could have been a little bit tighter together, but the values are correct, and that's what matters. And you can see that all cotangent curves are going to start, at least if they don't have a reflection, up here at their top, and then they go down to the bottom. Now, what I mean by a reflection is if we did have a negative out in front, we had learned with previous examples like logarithms and parabolas that those types of graphs end up reflecting. So this one would also reflect. But this would be one period of this graph. Now, if you wanted to draw a second period, okay, I actually made this a little wide, so I can't really probably go out and do it. But what I would want to do is go out another pi over 3. So maybe out to about here. Again, it would be the same distance from here to here as from here to here. I could just cut that back into quarters and then just repeat the pattern that I see here. And so I'll kind of do it. It's going to be a little tough to see just because of all the other stuff I have here. But if we go the first quarter, we saw that we went up to 3. The second quarter, we went up to 1 instead. And then the third quarter, we were down at negative 1. And again, these quarters are a little bit off, but hopefully you'll get the idea. And the graph will just continue to repeat itself.